Fundamental theorem of algebra. Let's look at that. We have seen linear equation as one root, quadratic equation has two roots, cubic equation has three roots. Now, what about a quartic equation? What about a quintic equation? What about equations of higher degrees? Or more generally, how many roots does an nth degree equation have? That last question is answered by this fundamental theorem of algebra. The theorem says every polynomial equation of degree n has exactly n roots, real or complex, and counting multiplicity. Now, the proof of this theorem involves higher mathematics. Hence, we discuss one of its applications. So, let's see applying the fundamental theorem of algebra. Now, let fn of x equal to this equation a sub naught x to the power of n plus a sub 1 x to the power of n minus 1 and so on up to plus a sub n is equal to 0. Let alpha 1 be one of its roots. And this is where this fundamental theorem of algebra guarantees the existence of alpha 1. So x is equal to alpha 1 is a root, which implies x minus alpha 1 is equal to 0, which implies x minus alpha 1 is a factor of the polynomial. And here we are using the factor theorem to make this statement, which implies x minus alpha 1 divides the polynomial, giving us a polynomial of n minus 1 degree. If you remember, we were trying to solve x cube plus x square minus 16x plus 20 is equal to 0. And by trying out small integer values, we arrived at x minus 2 as a factor. Then we, using long division, we divided x cube plus x square minus 16x plus 20 by x minus 2 to get x square plus 3x minus 10, which is exactly what this statement is talking about. X minus alpha 1 divides the polynomial, giving us a polynomial of n minus 1 degree. So it was a cubic polynomial. When we divide it by x minus 2, we get a lower degree, one lower degree polynomial. Therefore, f n of x is equal to x minus alpha 1 times f n minus 1 of x. Polynomial f sub n minus 1 of x again has roots, real or complex. How do we know that? Because FTA guarantees the existence. FTA means fundamental theorem of algebra. Now, let alpha 2 be one of its roots. Because FTA has already guaranteed that roots exist. How many roots? N minus 1 roots, real or complex, counting multiplicity. Let alpha 2 be one of its roots, which implies x minus alpha 2 divides f sub n minus 1 of x, which implies f sub n minus 1 of x is equal to x minus alpha 2 times f sub n minus 2 of x. With again, factor theorem we apply. Or in other words, that long division. The polynomial f sub n minus 2 of x again has roots, real or complex. Let alpha 3 be one of the roots, which implies x minus alpha 3 divides f sub n minus 2 of x, which implies f sub n minus 2 of x is equal to x minus alpha 3 times f sub n minus 3 of x. Again, factor theorem. So by repeatedly applying fundamental theorem of algebra and factor theorem, we get fn of x is equal to x minus alpha 1 times f sub n minus 1 of x. But this is what? This is x minus alpha 2 times f sub n minus 2 of x. But this is what? This is again x minus alpha 3 times f sub n minus 3 of x. So we break it down into its factors. So complete factorization is achieved. But ultimately we will reach a constant polynomial. So where a sub naught is a non-zero coefficient of x to the power of n. How can we say that a sub naught is a non-zero coefficient of x to the power of n? Because if we expand this by multiplying all the factors, the first term will be what? A sub naught times x times x times x times x times x. How many times? N times. So x times x times up to n times is nothing but x to the power of n. So we end up with a sub naught times x to the power of n, which means a sub naught is a non-zero coefficient of x to the power of n. Now, for each x equal to alpha 1 or alpha 2 or alpha 3 up to alpha n, the expression becomes 0. If we say x is equal to alpha 1 and the others are whatever, then what happens? X minus alpha 1 becomes 0 because we would have alpha 1 minus alpha 1. If this becomes 0, the entire thing becomes 0. So which means fn of x is equal to 0. Similarly, if x is equal to alpha 2, then we will have alpha 2 minus alpha 2. So this factor becomes 0, which means the entire thing becomes 0. So for each x equal to this, the expression becomes 0. Thus, fn of x can be expressed as the product of n linear factors. So that was fundamental theorem of algebra. That's it for now. Bye.